Assistant Professor of AEI Department of Netaji Subhash Engineering College. Today, I present a lecture on the topic Artificial Neural Network and its Learning Algorithms. In this lecture, I clearly focus on two distinct learning objectives. First, to identify the basic architecture of neural network with the traditional neuronal structure of humans. And second, is to illustrate the various learning algorithms involved in artificial neural network. Now, I link the learning objectives with Bloom's cognitive levels. As you can see that the first objective is mapped with the first cognitive level, which is called recall. And my second learning objective is mapped to the second level of Bloom's taxonomy, which is called understand. So now I gradually move forward to the topics which I am going to cover. First is neuronal structure and its artificial neural network architecture and the learning algorithms of artificial neural network. As you can see that this is a basic structure of neuron. This neuron has a cell body, a branching input called dendrite, and a branching output called axon. Axons are connected to dendrites via synapses. Electrochemical signals are propagated from the dendritic input through the cell body and down the axon to other neurons. Synapses usually vary in strength. Good connections allow a large signal, whereas slight connections allow only a weak signal. These synapses can be either excitatory or inhibitory. Now if you see the ANN architecture, you will find dendrites, cell body and axon. Here cell body has a threshold. This threshold is required during the firing of a neuron. A neuron only fires if its input signal exceeds a certain amount called the threshold in a short time period. Now I discuss 4 different learning processes of ANN, which is supervised, unsupervised, reinforcement and competitive. When it comes to supervised learning, you can see that there are a different combination of boxes from its design point of view as well as color perspective. Supervised learning techniques labels each of different boxes with a unique class label, each pair consisting of an input object, which is here box, and a desired output value, which is a class label, together forms a training set, and this training set is used for classification. These are some well-known supervised learning techniques used for classification purposes, such as linear classifiers, parametric, non-parametric, non-metric, and aggregation. Unlike supervised learning algorithm, unsupervised learning strategy forms different clusters, not different labels. And these clusters are formed by grouping similar kind of boxes. Here the similarity finding criteria is the color of the boxes. So instead of obtaining labeled response, this technique is used to find grouping in data. Now here is the list of various unsupervised learning techniques such as clustering, density estimation, and dimensionality reduction. Now comes to reinforcement learning, which allows machines and software agents to automatically determine the ideal behavior within a specific context in order to maximize its performance. Simple reward feedback is required for the agent to learn its behavior, which is known as the reinforcement signal. Here you can see the two examples of reinforcement learning strategy. One is playing chess and another is playing ping pong. In the former case, reward comes at the end of the game, whereas in the latter case, reward comes on each point scored. Now the last strategy is called competitive learning. This is a form of unsupervised training where output units are said to be in competition for an input pattern. These are the output units and these are in competition for a specific input pattern. During training, the output unit that provides the highest activation to a given input pattern is declared the winner and is moved closer to the input pattern, whereas the rest of the neurons are left unchanged. This strategy is also called the winner takes all strategy, since only the winning neuron is updated.
Now I have started with the portion where we have finished the previous class. That is a nonlinear separation by feed-forward neural network. And you can see that here we have one left-hand side structure, what is basically told as the architecture of the neuron. And obviously, you can see that what I have just mentioned, that we have three input signals or three input datas, you can say, or three input patterns, you can say, what is basically coming inside the neural net. And also we have W1, W2, and up to this, in this manner, Wn, the weight matrices, which are associated with each of the, input uh, data set or input patterns. So what we have here is, after this neural net, whatever be the output, that is automatically, fed to the nonlinear function, which is nothing but the activation function, and which is basically, based on this activation function, we are going to design our artificial neural net, and we can expect that how a neural net can work to, to classify all our output classes. So basically what we have here, that we have final one output section in case of this architecture of a neuron, where we have this the input sides are these x1 x2 up to xn, these are all input data patterns. And also the out is the output side or output layer, we can see in case of a particular neuron. Now if this is an architecture what I have just mentioning, then we can move forward to the symbol of a neuron, where we can expect this kind of neural net, and we are having this x1 w1, x2 w2, and xn up to xnwn. And inside this net, what we have, we can see here that we are going to take the summation of the product of this input pattern and its associated weights, so that we can have, Wixi as W1x1 plus W2x2 plus W3x3 and up to Wnxn here, and we are having one out. That means the output value we can see. Now what happens that whenever we have this kind of symbol of a neuron, so basically this is what we have studied as the feed forward neural topology, because here you can see that in case of feed forward neural topology, what we have just learned, that in that particular neural network, every time links are moving in only in one direction. So basically this is a feed forward neural topology, so automatically links are moving in the forward direction. So this is what we have here. That means this is what we can say as the input layer. This is what we can say the hidden layer, that means the intermediate layer between the input layer and the output layer. And finally this is what we can expect as out, and this is what we are calling that the output layer. So basically what we can have here, that we can have all the links which is coming forward from the previous node to the next next layer node, we can say. So basically here from this node we have three links which are moving to each of the nodes in the next layer, and again we are having two two links from each of the node which is which is available in the hidden layer. So the all these two links are moving forward to the next layer node, which is the output layer here, and automatically these two output layer finally gives out this out. That means this is the output of the classes. So basically whenever in this manner we can deal a particular classification problem by using this kind of feed-forward neural network, which involves the supervised learning algorithm. So basically all these output classes are also getting labeled. So that is why these two classes can be labeled as class 1 as well as class 2. So this is how a feed-forward neural topology looks like. Now, what happened whenever we are talking about this non-linear function? So automatically this function has certain non-linearity. So what kind of non-linearity we can deal with inside this non-linear function? This is nothing but hard and soft non-linearity. So hard and soft non-linearity means, if you can closely observe, that this is a one kind of step function, what we have already learned in control system and in any kind of sometimes in digital signal processing as well. So basically this is a kind of step function which we can term it as hard non-linearity. Why it is called hard? Because the if the out if the net value, that means net value means this value, net value means this value. So if the net value is greater than or equal to threshold, this particular value, then output is straight away is achieving 1. That means it is a very kind of hard technique, that the output is either 1 or 0. That means it cannot be differentiable, right? It cannot be differentiable. It cannot be having any kind of values between 1 and 0. It is either 0 or 1. So that is why this kind of non-linearity is basically a very hard non-linearity. On the contrary, we can also expect soft non-linearity. So soft non-linearity means we can expect this kind of output, output where we can have, you can see that this is a kind of similarity with the Gaussian distribution, what we already learned whenever we have completed the fuzzy. So basically what happens, that automatically you may experience also the output, the expression of this output variable in the Gaussian distribution manner. So basically every time whenever this net is approaching from this side to this side, you will be having a certain distinct value as the output, as the output variable. So what is the advantage of this soft soft non-linearity? I mean from this particular, I mean, as compared to that of the hard nonlinearity, that it is differentiable, right? It is not having only zeros and one values. It is not restricting itself between only two values, but it also gives you, a number of, different values whenever it is going to be, differentiable between this, I mean, 1 and 0. So basically, this is how the hard and soft nonlinearity works. So that is what the particular thing is described here, that this is, the step function. So sometimes it may happen that on the contrary with what we have here, that here we are having, out equal to 0 if the net is less than this threshold value. So for a particular step function, we can also have a certain value as well. I mean, not just 0, but we can have, a constant value as well. But obviously, constant value, it cannot be differentiable. It cannot be, more than one values for a particular, label. So that is why we can draw a step function like this as well. That means this is, some values which is 0. This is some kind of value which is having a, and this is a one kind of value which is having b as well. So here you can, draw the staircase or the step function. That means if your v, I mean, v is less than c, that means v is nothing but the net value. If this is, less than c, the output, that means this function, this output is having, a. And whenever this v, that means the net function, net value is greater than this c, that means if the particular v is having the value here or here or here or here in this zone, automatically it is achieving, that means the output value, output variable, that means the function of v, that is attaining a value of, a level of b. So this is one kind of step function where we are not confining ourselves between only 0 and 1, but we are confining ourselves between two distinct values. But every time it is not differentiable, what we can expect when we deal with soft, non-linear. So this is one kind of ramp function. So all these functions are very much, well known to you, because all these functions are, studied in case of control system. So basically here also, if we have this kind of, v function, so I mean, the output variable, which is the function of v, is attaining a if that v is less than c. That means if the v is attaining any kind of value which lies in this region, then the output variable must attain the value of a. Then it is a ramp function, that means it is a linearly ramp function when this particular v, is greater than, c, but obviously less than d. So in that particular case, basically this thing is, will be calculated as the output variable. And if, we have the net function, that is v, if that is greater than d, that means if the v is attaining any kind of value which lies in this region, then we can have, output variable can have the fixed value, again fixed level, as b. So this is ramp function. This is sigmoid function. This is also, well about this particular function, because we have also deal with this function in time of fuzzy. So this is one sigmoid function or Gaussian distribution, what we are usually call it. And obviously this is how you will get the output function, and that is the kind of, function you can see that we can have, I mean, we had in the previous slide whenever we have talked about the Gaussian distribution about the neural network, the activation function. So this is how your Gaussian function is like that. So basically by taking this sigmoidal step, that means the exponential value, this is one kind of, sigma parameter which is going to be considered whenever we have this Gaussian function, and this is a kind of normal distribution. This function always exhibits a normal distribution. That means you can experience in both half balanced search space, balanced data spreading. So whenever you will deal with this Gaussian function. Signum function, obviously, this is one also very popular function. This is a very simple function as it looks, but it has immense power, or and has immense importance in case of designing activation function, because this is one such function where if the net function, the net value is either it is greater than a 0, it will be having 1, and if it is less than 0, it will be having -1. So basically that is what the signum, that is the sign of z, is matter. I mean, sign of z matters most, because it is dealing with the sign which is associated with this 1. That means either it is positive or it is negative, and obviously based on this criteria, that means whether the net value is greater than or equal to 0, or the net value is less than 0. So in this manner, we can at least conclude, we can at least, now we can at least reach at a point where we can conclude that we have learned that the standard structure, what an artificial neural network can have, is basically comprising with the input units or input layers, which is basically the inputs as a fixed length vectors or the numbers, which is user defined, obviously, and some hidden units, which are the intermediate parts I have just mentioned between the input side and the output side, which basically calculates the threshold weighted sum of the inputs, and it can represent intermediate calculations that the network learns. Basically, whatever be the operational network, what an artificial neural network do, that will be done inside this hidden layer. Basically, there is basically the weight adaptation, weight adjustment, weight updation procedure will take place. You can all of this process you can experience in the next class. And obviously the output units, which represent the outputs as a fixed length vector, or the numbers as like the input units. So now we have come to an end of today's class, because I mean, from the next class, we are going to start with this particular slide, which is a single layer feed forward network, where you can see that there is no such hidden layer. You can see no such hidden layer. We have only input layer, and we have some output layer of neurons. That is why it is called single layer feed forward network. So basically these nodes, what I have just mentioned, that these nodes are nothing but the neurons, and obviously these arrows are the links or the signal flow direction from one layer to another layer. And obviously whenever the single layer becomes the multi-layer, so automatically this is how we can observe a particular feed forward network. That means hidden layer comes into the picture. So now basically we have come to an end of today's class. So till now, I mean, whatever we have learned, do you have any queries? You can ask me in any slide. Is it understood by all, or you can ask anything?